Last time we had finished this and the next slide after this. I just want to make sure that we start from the right place. So when the system, when the station comes on, Bluetooth station, it sends an inquiry or gets a page, one of the two, and then it gets connected to other device. Once it is connected, then it can keep transmitting, and most of the time is spent in this state, in this state, basically transmit state, and then it can go to sleep. And there are 3 levels of sleep: park, sniff, and hold. All right, so so hold is the least sleep. No asynchronous connection list. Synchronous connection oriented continues. Node can do something else, scan, page, or inquire. So if you remember, what is synchronous connection? So nobody has done any reading of anything, right? I mean, so it's basically synchronous is audio. If you're doing your headset or something, then in the hold state, that will continue. I mean, like that is totally allocated, right? And so you hold this connection, and then you can go and scan if see there's another device or something else that you want to connect to. So that is basically, I mean, this is like on a phone or somebody talking to somebody and say, hold, can you hold please for a minute? And so that's not really a sleep state. Second is sniff. Sniff is low power, and then you set up a time, and then you say, okay, I will listen again after so much time. Okay, so you know that you're going to come back. Okay, periodically. Park is gone forever kind of thing, very low power mode. It gives up its address, 3-bit address, and gets an 8-bit parked address and wakes up periodically to listen to beacons. And then it can just go to sleep and wake up whenever it wants to wake up and then see if there is something for it. Right? Generally, when I say whenever, I mean it cannot be more than a few seconds, because if you are using a device and it doesn't respond in a few seconds, you start throwing it around. So a few seconds is it can go to sleep for that much long time and then see if somebody else wants to connect or something else is happening. Okay. So that is the park state. This is the sniff state, and hold is simply, not active on the connection except for the audio. Everything else, discontinuous. Of course, no audio can happen in the other 2 states. You cannot be sniffing and doing anything like audio or in the park state. Only in the hold state you can do audio, but not any other data. Now, Bluetooth has a protocol stack which actually was designed even before they came into IEEE. So it's slightly different than what we are normally used to seeing, which is physical layer and PMD and MAC and so on and so forth. Here, the layers are RF, radio frequency, baseband, which is another thing which we would call physical layer, then the link manager, L2 cap, and then these things, which I will explain each of these one by one. And then on the top of that, we have application profiles. On this side, we have audio straight line from baseband to the application. And on this side, we have a host controller interface, which goes to the link manager. And then these are different things that the applications can use, different services. So we will talk about them one by one in the next slide. But this is nowhere close to what we are used to seeing in the IP world, where we talk about network layer IP and TCP and so on and so forth. There's none of that. Application goes straight through these layers. First, we talk about the address, which is in the baseband. RF we already talked about, by the way. RF is that hopping, right? So somehow the bits get there, but the question is, what does the frame look like? Before I talk about the frame, we talk about the address. And the address is 48-bit IEEE MAC address that is divided into 3 parts: upper part, non-significant part, and the lower part. So this adds up to 24-bit and this adds up to 24-bit. And if you remember the IEEE addresses, the first 2 bits are globally unique and multicast, right? First is multicast, second is the global or local. And then there are 22 bits of OUI. Anybody remembers OUI? OUI is organizationally unique identifier that tells you who made that device. So this 24-bit is exactly that. This 24-bit is OUI plus the 2 bits there. And this is really the device's address for that manufacturer. And this is what is used. So this is called the lower address part, LAP. This is the NAP and this is UAP. UAP and NAP combinedly make the OUI from IEEE. And this part is used to identify the PicoNet. So if I start a PicoNet myself, I will use my 24 bits, lowest 24 bits, to say that I'm the network number such and such. So there is some slight possibility that somebody else maybe have the same 24 bits because they might be from a different manufacturer, and each manufacturer has its own address assignment. All right, so but that is how you define the network. Network is defined by the lowest 24 bit, right? And we already talked about the clock running at 312 microsecond and the heart rate being twice as much, which is 625 microsecond. And so the key part in this slide is that out of the 48-bit address, so they don't use 64-bit as you'll see in a minute in the other technologies. This is one of the older technologies, and at that time, whenever this was started, 48-bit was still supposed to be good enough, big enough. So they used 48-bit, and out of that, they take 24-bit for the network to identify the network. Okay. In case of Wi-Fi, the whole 48-bit is used as the network for the network, right? So the whole and here it is 24-bit because this is smaller. I mean, maybe I don't know why they, but anyway. So the next layer is L2 cap. All right. So we have RF baseband. Actually, next layer is not L2 cap. Next layer is link manager, and link manager will come later. But L2 cap stands for logical link control and adaptation layer. Okay. So this is LLC part of Ethernet, logical link control. And what it does is exactly what LLC does is it allows you protocol multiplexing, segmentation reassembly, and quality of service. Now let us just see what is protocol multiplexing. So if a packet is coming through this protocol, when it gets out the other end, it will go through the same protocol. It will go from BNEP to BNEP, TCS to TCS, RFCOM to RFCOM, SDP to SDP. So that is called protocol multiplexing, taking many different protocols, putting into the packet, and all it generally these things do is they have a field which is protocol type, which indicates what is the payload type. So that is, and segmentation reassembly, if the packet size is smaller or bigger, then that part is handled in LLC, L2 cap here, and the quality of service things such as how much maximum bandwidth can this application use, what is the latency does it need, how much delay variation does it need. Host control interface is the chip independent interface to the Bluetooth chip, allows some software to run on all chips. So let's go back to that. So basically on the top of this, there is software. Actually, this is all software which is running here, and this is all in the hardware, and so this is what is really makes the interface hardware independent. Okay, it's like this. When you run Windows can be run on AMD machines, AMD CPUs, and can be run on Intel CPUs, but the same window. How does it run? because there is a layer called HAL, I think in case of Windows, HAL, Hardware Adaptation Layer. Hardware Adaptation Layer, that is what this is. This is Hardware Adaptation Layer. It hides the hardware from the operating system. In the case of Windows, the HAL hides the hardware. Basically, you can use the same kind of commands and it will translate. For AMD, it will do one thing. For Intel, it will say something else, so that the same effect happens, right? So this is host in controller interface. Then there is RFCOM. So now we are in the layer above logical link control, L2 cap. RFCOM presents a virtual serial port, sets up a connection to another RFCOM. Now, this is showing the age. Basically, is that when this protocol was developed, Bluetooth, at that time, the main way we did communication was through a serial port. Now we don't even have a serial port on the computers. But if you have some old computers, you will find some serial ports, 9-pin serial ports, right? And so this was one way to mimic that kind of I/O using a serial port. So this RFCOM allows you to connect a device which speaks a serial stream, and the other end, the serial stream will get out, and you will have a serial connection using two Bluetooth devices. RF communication, right? RFCOM. Okay. Then service discovery protocol. This is used to discover the services offered and their parameters. So every Bluetooth device offers a service. If you have a Bluetooth keyboard, it offers a keyboard service. If you have a Bluetooth headset, it offers the headset service. If you have a Bluetooth mouse, it offers the mouse service. And so this is the protocol which everybody speaks, so that they can figure out what you do and what I need. Okay, service discovery protocol. Network encapsulation protocol, Bluetooth network encapsulation protocol. Now this is basically network. Here is Ethernet and IP. If you have any data packets, they want to go over the Bluetooth, they will use this protocol, BNEP. So now let's see how much we have covered. So we have covered SDP for service discovery, RFCOM for serial port, and BNEP for Ethernet, etc. Right? Now TCS is still left. TCS is right here, but there are other protocols such as IRDA interoperability protocol, infrared. IR is infrared. Infrared IRDA protocol. So infrared was another serial port on the computer. So if you pick up a very old laptop, you might find it infrared port, a red color port on the back, and then that is how we used to connect to the printers. Printers had infrared port too. And so the infrared is like your remote control. It can work in the same room. If you're in the same room and aligned in the line of sight, infrared is light anyway, so it can communicate using light. So that is this one mimics that one, infrared, to work without changes. So the existing infrared devices or applications can work without changes, and there is a protocol called infrared object exchange and infrared mobile communication. This can be used for synchronization of IRDA devices. So if there are IRDA devices, they can connect to Bluetooth, pass over the Bluetooth to the other end, and then infrared can continue, right? So this is this protocol was not shown on the other picture somehow, right? IR infrared is not shown. But there is then audio is carried over SCO. We already talked about that. Audio, 64-bit audio over SCO links. SCO is that synchronous connection. And then we have telephony control specification binary, telephone control. So this is that TCS. This is for the telephony. And since the audio is going here, the control part goes through here. So the telephone needs two things. One is that you want to say, okay, ring, or connect, or disconnect. Those are all control. And once you start talking, that is audio. So that goes through that line. The control goes through here. All right. So TC telephony control implements call control, including group management, multiple extensions, call forwarding, and group calls. And then on the top of all this is application profiles. And they are called profiles because there are very strict limit on what an application can do. So the parameters are all set up in advance, basically globally. So if you have a headset, there are certain things that the headset should do, and every headset has to do that, right? So this is a headset profile. Okay. Then there is a keyboard profile. Every keyboard has to do that. Mouse profile, every mouse has to do that. And this is the only way they have such a good interoperability. Actually, Bluetooth interoperability right now is very good. You can buy any Bluetooth device and generally it works. Okay, with any other device. And that is because of these profiles. And so there is a lot of, if you read the Bluetooth specs, a lot of time or actually space is spent on the profiles, describing each profile. So there is a profile for headset, cardless telephony, intercom, LAN, fax, serial line, both RS-232 serial line and USB bus. So, universal serial bus. So basically, and there is much more basically. The profiles are keep going up and up because nowadays we have many more applications. And then here is a bigger list actually. Headset profile, GPS profile, hands-free profile, phone book profile, SIM profile, synchronization, video distribution, blood pressure, and and on and on and on. Okay. The main thing is that the device at both ends have to have the profile, and then they know exactly how they can talk using that profile. And he will hear this word profile from now on a lot in IoT because every protocol after this has followed that philosophy of having a profile for applications. All right, so there is one thing which we actually talked about, but we never called it that, link manager. Link manager is the one which takes you through all of these states. All right, so that is the one that manages the link when it is sleeping, when it is up, and when it is down, and everything else we talked about here anyway. Now, so let's see. So RF and baseband, this is the physical layer. This is the connection layer. This is L2 cap is the LLC, logical link control, which is protocol multiplexing and segmentation and reassembly. This is providing the hardware independence. This is the audio, and these are all the profiles for the applications. Okay. We could call this as the MAC. This is the actually part of the MAC. And there's no correspondence here basically because there's no routing, so there's no network layer, and everything is just one hop end to end, right? So right away we see the applications, and this is providing some reassembly which could be called part of the transport layer in IP world, and then we have these application services.